The position of the equilibrium can be expressed in numerical values. This is called KEQ, the equilibrium constant, and it's a ratio of product concentrations to reactant concentrations. So for this generic equation, KEQ would be equal to products raised to their powers, which are the coefficients in the balanced equation, divided by reactants raised to their powers. So the brackets indicate molarity, and K is going to tell us whether reactants or products are favored at equilibrium, and K has no units. So let's look at some examples here. In this first example, we're given the equilibrium concentrations of all reactants and products and asked to calculate KEQ. So K is equal to products, which in this reaction are H2O and CO, divided by reactants, H2 times CO2. We're going to plug in the concentrations. Concentration is moles divided by liter, and we're in a 1 liter flask. So my concentrations are 0.047 molar times 0.047 molar divided by 0.053 molar times 0.053 molar. K has no units, it's just a number. It comes out to, in this case, 0.79. And all that tells me is that at equilibrium, I have more reactants than I do products. Reactants are favored. Let's look at another example. This reversible equation, we're given the equilibrium concentrations of all reactants and products. Calculate KEQ. So K is equal to products in H3. It's going to be squared because of the coefficient of 2, divided by reactants, which are N2 times H2, and H2 would be cubed. Then we're going to plug in our numbers. Again, we're using molarity. So 0.1 molar squared divided by 0.25 molar, and then H2 is 0.15 molar, and that is cubed. Make sure when you enter this in your calculator, you square and you cube those numbers. So you solve it, and you get K is equal to a value of 12. Again, no units. Since K is greater than 1, products are favored at equilibrium. So I have more products than I do reactants at equilibrium. Next example says calculate KEQ for the reverse reaction in the previous example, assuming the same concentration. So K would be equal to, flipping everything around, N2 times H2 cubed. So nitrogen and hydrogen are products now because I'm flipping the reaction around, and NH3 is a reactant, so it goes on bottom. I'm going to plug in the same numbers. And I'm going to solve for K for the reverse reaction. For the reverse reaction, comes out to 0.083. And so the question is, how is KEQ for a forward related to KEQ for a reverse? Well, they're inverses of one another. And what that means is this: if I take 1 divided by 0.083, I get 12. They're inverses. One more example with K. We have the following balanced equation. We're given the equilibrium constant K is 11.1. We're looking for the equilibrium concentration of BrCl. So we have K is equal to products, Br2, times Cl2, divided by reactants, which are BrCl, and that is squared. Okay, we're given the value for K is 11.1. We're going to set that equal to concentrations we know are 4 times 4 and we're solving for BrCl. Okay, you can do a little rearranging here. So I know the concentration of BrCl squared is going to be equal to 4 times 4 divided by 11.1. Rearranging that equation, so the concentration of BrCl is equal to the square root of 16 divided by 11.1, 1.2 molar is the concentration of BrCl. So we solve for K, the equilibrium constant. There's also a reaction quotient, Q. This is the number obtained by substituting starting reactant and product concentrations. Q and K take on the same form, products divided by reactants, except Q uses starting concentrations. K uses equilibrium concentrations. If I compare Q to K, it will tell me which way the reaction will proceed, either toward reactants or toward products, in order to reach equilibrium. So let me look at an example with Q. The question is, predict the direction the reaction will proceed in order to reach equilibrium. So I need to solve for Q. Q is equal to, go back to my balanced equation up here, products, HI squared, divided by reactants, which are H2 and I2. So plug in the numbers. These are starting concentrations. So we've got 0.01 molar squared divided by 0.005 times 0.015 molar. Solve this for Q. Q comes out to a value of, and it is unitless, 1.33. I'm told that K is equal to 50. So if I compare Q to K, Q is obviously less than K. 1.3 is less than 50. So this reaction will proceed toward products. I will produce more products in order to reach equilibrium.